Hey, we made a cobweb diagram or a staircase diagram. It's a staircase diagram when you see things doing that sort of thing, and some people call it a cobweb diagram when it does that sort of thing. Obviously, I'm changing the number of iterations of this, and because it's GeoGebra, it's interactive, I can change the starting point, and that's pretty. And because I built a function that had a parameter in it, I can change the parameter and see some interesting behavior with other parameters, and we can crank up the number of iterations. So this is the sort of thing that's really useful if you want to teach an iterative method of solving an equation. This is the classic just self-iteration of an equation to find a root of it, and I'm going to show you how I built it. So I've been recording the intros to these videos after I've made the file. I haven't made anything yet. I hope you've seen what I'm going to try and make now, because it's a cobweb diagram or a staircase diagram. This is a really nice topic that still turns up at A-level maths in the UK. It even gets a glimpse at GCSE, using iteration to solve an equation, whether or not you could solve the equation by another method. So quadratic equation you could solve with all sorts of methods. I'm sure you can pick your favorite. Quadratic formula, factorizing, complete the square, that's my favorite. Cubics, there is a formula. I'm not going to show you that. That's Derek's just done a recent video all about the history of that wonderful stuff. But you can solve equations that you can't solve with a closed formula by using a numerical method, in this case, a fixed point iteration. And this is going to tie really nicely in with the video I last did on the bifurcation diagram, because that was a fixed point iteration thing as well. So let's build a file that solves equations and shows us visually what's going on, which is quite often called a cobweb diagram or a staircase diagram. And you'll see why those names are appropriate if you don't already know. And I'm going to use, at least to start with, the same function I did in the previous video on the logistic map. I'm going to use the logistic map and find fixed points of that. So let's start by getting the Geogebra window up. I think everything's working all right. So this is the Jojoba Window, Geogebra Classic 5, and other versions are available, other packages are available, but we can build this quite easily in Geogebra, and that's pleasing. Let's start by getting a function. Let's call it f of x, and I'm going to use a parameter a, and not every equation will have a parameter in. This is going to let us play around with it later. I could add it in later. That's my function a times x times 1 minus x. It's asking for a slider for a, and I will limit that to between 0 and 4 for this, and the previous video goes into why I'll do that. Let's just get that done. This time I do want to see the function. Last time I hid it, but you can see changing a changes that. Let's zoom in a little bit. That was with the shift right drag, by the way, and you see that's just adjusting the parameter in there. It's a fairly simple looking quadratic, and what I'm looking for is a way of finding when the output of that function is the same as the input, i.e. what they call a fixed point, and that would be where that graph crosses the line y equals x, because that's when the y coordinate is the same as x coordinate. So let's plot the line y equals x. Let's call that g of x. Here it is. This has two fixed points, one at 0. If you put 0 into that function, you'll get 0 out. Hooray! And if you put just above 0.7 in, apparently you'll get just above 0.7 out. That's because that's where they cross. So this diagram is intending to find the solution to where a function equals x. Function of x equals x, which is called a fixed point. And maybe I'll do a demo later on of how to take just a random equation and turn it into a form you can use to solve in this way. But let's build the thing. First, what we need to do for this iteration is specify a start point. And I could just type a number in. I'm actually going to do it visually, so we've got a sort of interactive way. I'm going to drag this point A around. Now I've clicked on the axis there, and I can drag it around. It's attached to the axis. If you wanted to do that, by the way, the long way, you could type the command point, and then you can say x-axis. It's worth knowing that the axes in GeoGebra are referred to by the letter, and then capital A, followed by the word axis, and that would also put a point on the axis. And you can see that point B is on the axis. It's attached there. You can attach things later on, and the clicking version is just as good as anything else. Now, I don't really care that it's on the x-axis. All I really want here is this is a visual starting point on the x-axis. I don't really care that it's on the x-axis. It could have been up and down. It doesn't really matter. So I just want the x-coordinate of that, and that might be useful. I'll specify that as the starting point, st, and you can get an x-coordinate of a point by doing x of a point. That's a nice function. That's almost so neat in GeoGebra that it's easy to forget. Or hard to find if you didn't know what it does, and you can get the y coordinate in a similar way. So that's my starting point. I've happened to have nailed it on 0.5, but you can move it around anywhere. Obviously, I'm expecting this to converge to this point here, or this point here. We'll talk about why it doesn't do both. You'll see in a bit. But it's not there yet, so I'm going to leave it far away. And the point of this iteration is that you put a number into the function, and then you take the output and you put that back into the function. And visually, that is the same as going up from this point to the function. That's literally what putting a number into a function does. And then I'm going to track across to the line y equals x, because that's where you change the output that you just had, which was the y, and put it back in for the new x. So you're making y equal to x and then putting it back in. So once I track across to the y equals x line, I go up to the function or down to the function, depending on where it is. And you can see already that as I do that, it's going towards that solution. If I go up there, it might go towards, or it might bounce around a bit. Let's draw this, because doing it just by dragging this cross around is not the whole point. We could start sketching. I could put the point, and this is really important, st for my starting point, comma f of st. Let's get that right. And it's done that point, and it's really important to recognize that's what a point on a function is. It's x, comma f of x. In this case, I've used st, and that moves around with it. There's a point on a function, but then I would keep having to type it in. And so what I want to do is make a way of making a list to make this, do it repeatedly like n times, and I can have a slider for n and make that work. That's my plan, so I don't want the point B. What I do want is the list of values that get me there. And actually, the command we used before in other videos, iteration list, is going to do this. So this is what the iteration command does in Geogebra. It repeatedly iterates a function, puts a value in, gets a value out, puts it back in. And the iteration list keeps a record in the list of all of the inputs and outputs, or the outputs technically. So let's do an iteration list of the function f. Let's start at st. And let's go for a number of iterations n, and I will need a slider for n. Thank you, Jojoba. You've offered to make me a slider, but I will make the slider go from 1 to, I don't know, let's go up to 100 in ones. And doesn't do anything yet. Oh, no, it does. The list exists. It's already iterating it. So Jojoba's doing the iteration for us. I didn't need to do anything. The iteration list commands works really well. What I want to do is make that visual. So what I need is to turn these points in here, which if I drag this onto the screen, you can see the list is already quite long. It's 36 long. And it is not converging. Interesting. Well, I do know why that is. Now it is. You can see this iteration list is homed in on 0.55. More on that when we can see what's going on. I don't really need that list on there, but I need the points. These are just numbers. So what I need is those x values and where they fit on the function. So let's make a list of points that do that. And I think that's going to be fine. But if I just zip, I want a point, which is, I'm going to use capital X and then f of capital X. And I'm going to tell it that capital X should come from the list I've just made, L1. I think that's going to do it. As soon as I delete all these bits I don't need, we're going to see some points appear. There we go. I can't see loads of them because they've homed in really quick. What I really want to do, though, is see the joining paths. And you already begin to see why I might call this a staircase diagram. So let's see if we can make a list that does that for us. And this is maybe the fiddly bit, which is why a cobweb diagram or a staircase diagram is hard to make quickly until you've done a little bit of thinking. But this idea of using lists is still going to work for us. We've got all the points. We just need to join them together. So I'm going to do the vertical lines separately from the horizontal lines. I think that's going to help us rather than trying to do them both at once. I haven't got the points on the f of x. So actually, maybe I should get the points on f of x. Let's get another list. I'm going to zip again. This time I want x, comma x, where x is from that list L1. And that's just going to give me the same points along the y equals x line. I hope, yeah, that's looking promising. It's giving me one I don't need. That first one starts on the axis, which is a bit of a glitch in our system. So let's just take the last of all that list, n-1 elements. Why is that not? So maybe I need n, the last n. Maybe the list has n plus 1 elements. Why does that happen? Yes, because there's a starting point. If I do plus 1, I get that one. Interesting. I haven't quite figured out why the list is length n plus 1. I guess that's what iteration list does. It does n more iterations, and my starting point is in there. Anyway, those dots are useful. I still would like to join them up, so let's now make a list of vertical lines, which I think is going to be a question of joining. You can see these two lists. If I drag these onto the screen, those two, they're sort of lined up. I want to join that. What do I want to join? I join the starting point. So what I'd like to do is have the starting point in there as well as my first point. So let's get that in there. Clicking on the text of the list doesn't help. So actually define this list. I'm taking the last. I'm gonna join some lists together in one command. I'm going to say that use the word join, which takes some lists, and all I'm going to do is add a list, a single element list, which is the point A, starting point there, and I think that will join them. Look at that. You can't see it, but that's what I wanted, because now I think all the vertical lines I want are literally the joining of L3 with L2, which is going to make it super easy to do. So let's zip along those two. This time we're going to use two lists on our zip. Let's get a segment between point. What shall I use? I don't want to use A. I was about to use capital A, but there's already an A in here. So let's use P and Q. Point P and point Q. P wants to come from L3, and Q wants to come from L2. I think that's it. I think we're going to see the vertical lines. Yes, it's always a relief. That's the vertical lines joining the points. So this looks like it's doing what I want, but we still want the full picture of the joining up at the base of them. So let's do another one. Let's zip together segments again from P and Q. Again, I can reuse this. They're kind of dummy variables as long as it's not thinking they already exist. With P from, now how do we get this right? I just want the same two lists, but if I sort of shift them by one, we'll get it right. And this time it's going to go from L2, which are the ones on the function, to L3, but I want to drop the first one. So let's take the last. Q come from the last. Because I've a slightly ham-fisted way of doing this, but the last of L3 N, I think, is what we want. I think that's doing what we want. Let's just take n-1 in there. That doesn't work. And n+1. No. So that's what we want. And if you can't see why it's called a staircase diagram, I don't know how to make it more obvious for you. My zoom didn't work there. Strange. Make sure you press escape. There we go. That's working now. So there's the staircase. This is homing in on that point. It is not homing on this route down here. In fact, if you go the other side of that, this does not converge. And if you look at let's do another command. Let's do the iteration without iteration list of F. This is exactly the same as before, but without doing the whole list iterations. You can see that it's converging to -infinity, whereas this time it converges to 0.55, which is what we expected. It does it the same here. And now we've built this. This is kind of where we're heading to all along, just some detailed aesthetics now. But you can see changing the parameter changes the behavior of this. And this is what we were looking at last time in the bifurcation diagram. Sometimes this iteration converges nicely. Sometimes it converges on 0. It does converge down there if there's only one root, in fact. But when there are two roots, it converges on the higher one. And actually, when you go past 3, you get a situation where this does not converge on a root. It actually bounces around two stable points, which are not the root. And depending on how close to the root you start, it sort of actually diverges away from that root. So that fixed point becomes unstable. In fact, you get a 2 cycle around it. And if you remember from last time, what happens when we go beyond this sort of value of A, we do get some crazy behavior. And this is the cobweb diagram of that bifurcation logistic diagram we were looking at last time. All very nice. Now, aesthetic things, maybe I don't want the dots, but they're easy because I built them in just in lists, so I can turn the dots off and we just get the lines if you like that sort of thing. We could change some colors. We could just let A animate and we could let... Anyway, so the point is it's done. The zip commands and the list commands are really useful here. Let's do a final tiny bit of maths then. Let's say we were going to solve an equation. And if we want to solve an equation, we should write down the equation. So let's find a way of writing this down. It's just a one-note screen here. I had one in mind. So the one we were just solving was actually this equation. X equals A times, I don't need the times, do I? X, 1 minus X. And I was worried about this one because that's the function I want to find a fixed point of. But the other application of this and what they sort of want you to know about at A level is like, so let's say you had an equation X to the 5. I'm making this up to a certain extent. I think I remember wanting to use a half for reasons that will become apparent I hope. Let's say this is an equation, and you can't solve this equation using a quintic formula. It's a quintic equation. It's not quadratic, cubic, quartic. It's a quintic. There is no quintic formula. And I'll go and ask Galois, not that he's still alive, if you want to know more about that. How can you solve it, though? If by hook or by crook you need to get an answer where that is true, then it's the same as asking this. If you rearrange this, I could easily rearrange to get x equals x to the 5 minus a half. So it's the same equation, and the point is that that's looking a little bit more like the format I had earlier, where x equals another function of x, which means I could just type that formula into my Cobweb diagram solver that I've just made, and hopefully it will show me if it can solve it. The ones that are familiar with this may know there's a problem coming. Let's see what that problem is. So what did I say my function was? X to the 5 minus 0.5. I think that was it. Is that right? Yeah, let's try that. And here we have, the graph is clearly saying it crosses 3 times, 1 and then 2 down here. And this thing is homing in on that. So it's finding one of the roots, but it is not finding that root, and it is not finding that root, because if I try and go near it, it doesn't do what I expected. So it is kind of working, but it's not finding 3 of the roots. In fact, there are 5 roots. 2 of them are complex, and that's the fundamental theorem of algebra, which we won't go into right here. But you can see that there were other choices. This was an arbitrary choice of how to rearrange it. So if, for example, I chose to instead rearrange it to say x to the 5 is the same as, what would be x plus a half, then I wanted the form x equals, so I'd have to do the 5th root. So x equals the 5th root of x to the x plus a half. And to be honest, I'd probably prefer to write it like this, because this is how computers are easier to type in, as long as you're happy with fractional exponents. Let's do that, and it should give us the same 3 roots. So just under -0.8, just under -0.6, and just about 1.1. Let's see what happens. Only one of the roots was being found by this Cobweb. So was it the 5th root of x plus 0.5? Let's put some brackets in appropriately. Power of 105. And lo and behold, they are there, these 3 roots. And it's now finding this one. That's nice, in a nice staircasey way. And does it find any others? Even if I go near this one? No, it seems to diverge from that one and find the one up there. But it does find that one. So this is a nice demonstration that I could use this. Here are the answers, by the way. 1.1, it's converging there. And if I take a different starting point, -0.77. And if I go back to the original one, I could get the other one. What was it? X to the 5 minus r. I think that's what it was. Yeah, there we go. And this time it's fine, -0.55. Those are the 3 roots. I'm pretty confident because it is converging. And this Cobweb diagram I built is demonstrating it nicely. The reason I wanted to do this here is, if I go back to the original logistic map, is it is the sort of companion diagram that goes with the diagram that we produced last time, the bifurcation diagram. That diagram was plotting the fixed points as you change the parameter a. But what this is doing is showing the behavior of the iteration itself. And so when a is actually low enough, we get stable iteration, kind of boring staircase. Hey, it's solving an equation. That's kind of what you want iteration to do in that context. Sometimes it solves it to equal 0, but beyond 3, you get unstable iteration. It sort of cycles around, and then you go beyond that and you get into these crazy cycles. So one thing that might be nice to finish off with, I could actually get an attempt for it to count how many values are in the cycle here. This one is bouncing around all over the place, but I know that, for example, just above 3, it's a 2 cycle. You can see it sort of bouncing around in a rectangle. And that's hard to tell at the moment. So what I might do is look at this long list of the iteration list. I could look at the last few values of it, say the last 20, and see how many unique values in there. I'm going to round it. This is a numerical method after all. And if it's only got 1 unique value, I feel like it's claiming it's a 1 cycle or a fixed point. And if there are 2, then we know it's a 2 cycle. So there's a way to do that, and it's just nice to demonstrate perhaps. Let's see if it will do it on this. We're expecting a 2 cycle at this stage. So what I'm going to do is grab the last 20 from L1. I think it wanted it like that. And you can see it's looking promising, 0.76, 0.56, 0.76. So maybe I make sure that's rounded. You can round a list. So I'm going to round that to 2 decimal places. Just to prove that it is doing that, if I crank up the rounding to, I don't know, 5, and just change this definition back again. Well, let's do 1 decimal place. It's rounding it there, and I can round it to 3 decimal places, and it is doing that. Let's leave it at 3. Maybe it's accurate enough. And then all I want to do is find out how many unique values are in that list. So there's a command called unique, which just finds actually puts into a list the unique values. So if I do L6, then it does that. Those are the 2 values. And actually what I really want to do is find the length of that. And the length of that is just length L7. So that value there, I can drag onto the screen, is telling me how many cycles it's settled into. Now, it's a numerical method. It won't be perfect, I expect. Let's see what happens. So over here, I mean, this is the same iteration. So let's just change the parameter again. We're expecting a 1 cycle back here. There we go. 1 fixed point. We'll probably go into a 2 cycle just beyond 3. There we go. And then a 4 cycle eventually, but it might, there's a 4. That's nice. I think it's then going to struggle because I'm only checking the last 20, and this is going to go quickly beyond 20. So we've got, we should have had an 8 in there somewhere, but I've got very big increments going on. And then it's just saying 20 because that's the length of the list I'm checking. That's enough, I think, for now. This is a nice demonstration, and it's already a pretty picture. Let's just zoom in on it and make the most of it. I've not demonstrated loads of aesthetic tinkering on this. You can make it look the colours you want, change the backgrounds and all sorts of things. But building a cobweb diagram itself is not too hard, particularly when you've mastered the sequence and zip commands to handle lists like this. You could also do it in the spreadsheet. And in fact, when I originally made a file like this, I would do it in the spreadsheet, but I find it cleaner and nicer to use list commands because then you can have a slider controlling the length of the list, and that's really nice. I hope you've been interested in this one. This is the cobweb diagrams or staircase diagrams. This one looks more like a cobweb now. You can see where the name comes from. As ever, if you have suggestions of other files I should make live on this channel, then please let me know, and I'll see you next time.